Okay, let's take a look at section 7.2 where we're looking at radical functions. A radical function is a function that contains one or more radical expressions. We evaluate radical functions by substituting the given value for the variable and simplifying using the order of operations. So on number 1, if we want to find f of 76 when f of x is the square root of x plus 5, we simply do what you learned at the beginning of the semester and even in introductory algebra. We basically replace the x with 76. Now, a radical is considered a type of grouping, so I have to add 76 and 5 before I apply the radical. Those are grouped together inside the radical. So this is the principal square root of 81, which is the positive number 9. In number 2, f of x is the square root of 6x plus 1. When I want to find f of 4/3, I simply replace x with 4/3. Remembering that the square root is a grouping, so I have to complete the operations inside of it before I'm able to apply the square root. So 6 times 4/3, I can actually divide the 3 into the 6 and I get 2. So this becomes the square root of 2 times 4 plus 1, which is the square root of 8 plus 1, which is the square root of 9, which is 3. So the principal, a lot of times we simply say square root instead of saying principal square root. Here our radical function is the cube root of 4x minus 5. So when I want to find f of negative 11 halves, I do what I did in the previous 2 problems. I replace the x with this value, which in this case is 11 over 2. And I, again, understand that the cube root, any radical, is a grouping. So I have to complete the operations inside. So 4 goes into 2 twice, and I wind up with 2 times negative 11 minus 5 as my radicand. This is the cube root of negative 22 minus 5, which is the cube root of negative 27, which is negative 3, since negative 3 times negative 3 times negative 3 is negative 27. So notice I don't run into any issue when my radicand, which in this case is the negative 27, is negative if the index, which is in this case the 3, of the radical is odd. All right, we want to evaluate f of 20 for f of x equals the 4th root of 4 minus x. So this is the 4th root of 4 minus 20, which is the 4th root of negative 16. And I'm told if the value is not a real number, state so. So this is not a real number. There is no real number that, when raised to the even power of 4, will give me negative 16. Later we'll talk about taking square roots of negative numbers and what it's not a real number. What is it? We'll talk about that. All right, if the index of a radical function is even, the radicand must be greater than or equal to 0. If the index of a radical function is odd, the radicand can be any real number. So in other words, when I'm dealing with functions, in order for my function to be defined at a particular value, the result has got to be a real number. So if I apply an even rooted radical to a negative number, the function is undefined because so in this case here, f of 20, since f of 20 gives me something that's not a real number, I would actually say f of 20 is undefined. So in order for a function to be defined in our scope of learning, the result, when I put a value into the function, has to be a real number. All right, I want to find the domain of f of x, which equals the cube root of 4x minus 5. Whenever the index is odd, the domain of my radical function is always the set of all real numbers. So notice 3 is odd. I'm asked to show some steps here, so I'll say 3 is odd. So that's my first step. And that basically means 4x minus 5 can be any real number value. So therefore my domain is all real numbers. And I'm going to give that as an interval. Now when I want to find the domain in number 6, and I see I have a fourth root, here the index is 4, and that's even. Now what's inside of the radical, in order for the function to be defined, which means the function value is a real number, has to be greater than 0. So 4, or equal to 0. So 4 minus x has to be greater than or equal to 0. So I'll simplify this inequality by adding x to both sides. And that means 4 has to be greater than or equal to x. Now that's the same as saying x is less than or equal to 4. Let's look at graphing radicals. And when I graph a radical function, if the index is even, then I'm going to have a place where this starts. Now in this case, since the radicand is x minus 1, and I need that to be greater than or equal to 0, then that if I add 1 to both sides, I get x is greater than or equal to 1. So this is going to start when x is equal to 1. So when x is 1, I get negative 2 times the square root of 1 minus 1, which is the square root of 0. So when x is 1, I get 0. So that's actually my starting point. So when a radical has an even index, it always has a starting point. If its radicand can be negative. I need to add that. Here, when x is 2, I have negative 2 times the square root of 2 minus 1, which is the square root of 1. Or that's negative 2 times 1, so that's negative 2. So when x is 2, this is at negative 2. When x is 5, I have negative 2 times the square root of 5 minus 1, which is the square root of 4. So that's negative 2 times 2, which is negative 4. So when x is 5, y is negative 4. Notice how I'm plotting. So these are the points I'm plotting. 1, 0, 2, negative 2, 5, negative 4. And now I'm going to let x equal 10. So I get negative 2 times the square root of 10 minus 1, which is the square root of 9, which is 3. So negative 2 times 3 is 6. So I'm going to plot the point 10, 6. I'm sorry, negative 6. 10, negative 6. So when x is 10, y is a negative 6. And this would actually continue forever. I, however, have run out of graph. So the graph is this smooth curve that looks like this. And it's hard for me to draw on this electronic tablet. So let me just show you a nice picture of that graph. Okay, so this would be a much nicer curve showing you what this looks like if I was able to, draw it more carefully. So this is actually what it would look like. So here's what the graph would look like if I was able to actually draw it in a more exact and more controlled way. All right, and then similarly, we want to graph this cube root. Now, in the case of an even index radical, we don't have an issue about domain. All the real numbers are the domain of this. So I don't have this limitation as to what I can put in. So we're going to look at the results if x is these values. So if x is negative 6, I have a y that's the cube root of negative 6 minus 2, which is negative 8, plus 3, which is, and let me see, I'm going to maybe come down here and do this. So f of negative 6 is the cube root of negative 8. Negative 6 minus 2 is negative 8 plus 3. So that's negative 2 plus 3, so I get 1. So I'm going to be plotting the point negative 6, 1. If x is 1, I get the cube root of negative 1. 1 minus 2 is negative 1 plus 3. So negative 1 plus 3 is 2. So I get a 2 when x is 1. F of 2 is the cube root of 2 minus 2, which is 0, plus 3. The cube root of 0 is just 0, so this is 3. When x is 3, I get the cube root of 3 minus 2, which is 1, so the cube root of 1 plus 3, which is 1 plus 3, which is 4. And then when x is 10, I get the cube root of 10 minus 2, which is 8, plus 3. The cube root of 8 is 2. 2 is the number that cubes to give me 8. So the cube root of 8 is 2. So I get 5 here. So I'm going to plot the point 10, 5. So let's plot these points. Negative 6, 1, 1, 2, 2, 3, 3, 4, and 10, 5. All right, so we get a picture of what this looks like. And notice how the shape is a little different from what we saw in the other case. All right, and again, let me show you a better picture of that. Okay, so here's my attempt at drawing this, given my limitations with this electronic pen. But let's look at a better graph. Okay, so here's what the graph would look like if you could actually draw it extremely accurately. It would look like this. And we see that we have that to a certain degree, but it doesn't look as precise as we would like. This is a brief summary of the main concepts in section 7.2.